is 4.184 joule to make 1 calorie. So if you have 8.32 calories, understand that the entire universe is made up of the system and the surroundings. Therefore, looking at the system is part of the universe under study or the object of your study. For example, if you are cooking in your room, the stove or the gas you are using and the pot you are placed upon the cooker could be seen as a system. And if you want to also to extend it, you can say the room or the kitchen where you are cooking is your system. So you need to define your system. If you're carrying out an experiment in the laboratory, what you are using, maybe you are using a test tube or you are using a beaker, that becomes your system. So you need to define your system. And the boundary is an imaginary or a real surface that separates the system from the surroundings. So it puts a difference between the surroundings and then the system. And your universe comprises of the system and the surroundings. So we can say that the universe is surroundings. I hope you're getting me. So the remaining part of the system, you have your system. Anything outside your system is the surroundings. And that one is not under study. That is where you make your observation. Like you place your practical notebook and you are writing something down. So anything outside your system is the surroundings. That's where you make your observation. Of energy, what we say is that total energy of an isolated system. So for brevity, total energy of a system, of an isolated system, is constant. So it states that in physical or chemical change, energy may be exchanged between a system and its surroundings, but energy cannot be created or destroyed. Energy may be converted from one form to another, but the total quantity of energy remains constant. So the energy of the universe remains unchanged and is therefore constant. So like I told you, the total energy of an isolated system is constant. That's the law of conservation of energy. Now, so in equation form, it means the delta E, which is change in energy of the universe, equals 0. Nothing goes in, nothing comes out. So the total energy of the universe is constant. It is not created or destroyed. However, it can be transferred from one substance to another. So if you want to now look at the total energy of the system of a universe, so it's the change in the energy of the system, but the change in the energy of the surroundings. Remember, I told you that your universe is made up of the system and your surroundings. And your system is where is what you are, the object of your study, and your surroundings is the immediate environment outside your system where you are making your observation. Number 3, we have an isolated system. Now, if you look at the 3 test tubes, you will see that the open system, it allows heat to come out. It allows, that is, heat transfer to go out or to come in. So that is exchange between the system and the surroundings. And if you look at the second test tube, where you will see closed system, it allows it transfer. So it can come in, the transfer can come in, and then, but it may not, but does not really allow free passage. To the surroundings. So you will see that one, that test tube. You see in the open test tube. And the closed system, energy can cross the boundary, but matter cannot. You know, we have told you matter is anything that occupies space and has mass. So energy goes in, but matter cannot. So for example, now if you have a sealed test tubes, like a bottle of water, there will be exchange of heat, but water that is inside cannot come out. Cannot come out. So that's the. Now you look at the third one, the isolated system. Both matter and energy cannot cross between the system and the surroundings. It cannot. It is isolated. And that's why we said that as an example, the universe are made of the surroundings and the system is an isolated system. And in such an isolated system, the total energy of that system is constant. Please, you need to note that. So there are no surroundings to exchange matter or energy with, as far as an isolated system is concerned. Let's move ahead. Now, when we are talking about a state in chemistry, you are talking about the condition of the system. You are talking about the condition of the system at any given specified, at any given time, and they are specified by some variables. For example, in an equation, the ideal gas equation, where you will see PV equals nRT. So where P is the pressure, the V volume, your N number of moles, your R universal gas constant, and then your T the temperature. So for you to know one, then for you to determine one, then you must know the quantity of the others. Then from there, we look at homogeneous and heterogeneous system. When we say something is homogeneous, they are uniform, they are in the same phase. So for an homogeneous system, it is a system that is uniform throughout. That is, it consists of only one phase. For example, you may have a system containing only pure solid, or you have a system containing only pure liquid or pure gas, or they are completely miscible liquids or gases, not immiscible. Miscible liquids or gases, you can correct that, miscible. So they are in the same phase. They are liquid throughout. They are liquids throughout. Or they are gaseous throughout. Or they are solid throughout. So it is miscible, not immiscible. Now for heterogeneous system, it's saying that it is not uniform. That is, it is more than one phase. It is more than one. It is polyphase. For example, you have a mixture of two immiscible liquids, or gases, or solids. So they are not miscible. They are not miscible. You have water, you have oil. So then we also look at thermodynamic properties. Thermodynamic properties. For example, we have intensive properties. Intensive properties. These are properties that are dependent or quantity of matter or the material present in the system. They depend on the nature of the material in the system. I will repeat myself again. These are properties that are not dependent on the quantity or the amount of material or matter in a system, they are dependent on the nature of the material in the system. For example, we have viscosity. Assuming you put a viscous substance probably in a container, small container, and you have the same type of viscous material in a bigger container, the viscosity will be the same, irrespective of the amount that is there. The viscosity in that small container will be the same thing as the viscosity in that bigger container. The same thing with surface tension. Same thing goes with thermal conductivity or temperature. For temperature, maybe you have water that is about 100 degrees Celsius. You put it in a small container, and then you also have it also in a bigger container. If you say because the first container is smaller than the bigger one, you say that therefore the heat must have reduced. If you put your hands inside the small container, you will notice that you will find out that they are the same. So that shows that this property of the system dependent on the nature of the matter in the system. Same thing goes for density and specific heat capacity. Then extensive properties. These depend on the amount of matter in the system. For example, mass, internal energy, heat capacity, free energy, heat content, entropy, etc. So that one depends on the amount of what is inside. So for extensive properties, the bigger the amount, then that will also determine how the property. So it's that the property is. Then we also have thermodynamic processes. These are the processes that bring about changes in the state of the system. That it brings a change, that the processes that brings about a change in the system, and there are different types. Number one, we could have a isothermal process. The temperature remains constant throughout the process. Isothermal, constant heat, constant, it is constant. Nothing, there is no change in temperature. So the delta T, the change in temperature equals 0. Then we also have a process that is and the system, there is no, so the dq is 0. The Q is 0. Let's move ahead. We have isobaric process. Isobaric process, that is the pressure remains constant throughout the process. The P equals 0. The P equals 0. We have an isochoric process. That means that the volume remains constant throughout the process. dV equals 0. That is, the change in volume is 0. The change in volume is 0. We also have a cyclic process. And that is a process undergone by a system. That is when a system in a given initial state, it goes through a number of different changes, of different steps. That is going through various processes, and at the end of the day, it returns to its initial value. That is cyclic. You are moving from, maybe from your room, you go through so many places, partly you come to UI, from UI you go to other places, and then you return again to your room. So it is when a system in a given initial state goes through a number of different changes in a state, or going through various processes, and finally returns to its initial value. So we can say that the system has undergone a cyclic process or a cycle. So, and at the end of the day, we can say that all the properties of the system, they are still the same. So it means at the conclusion of the process, all the properties have the same value they had at the beginning. The delta E equals 0. We also have what is called path function. Path function is the property whose change depends upon the path that is followed by each, and not on the place. You need to understand that it's different from the one we earlier defined as cyclic process, which is just you move through certain changes and then you go back to the same place where you started, to your initial place where you started from. It's different from the path function because this is a function of the path that you follow. For example, we have a work. We have work. That one depends on the how you start, on the path you took before coming to the final stage. Then we have a state function. State function. When we say something is a state function, that shows that that particular thing is dependent upon the initial and final state of the system. And it does not depend on the path it follows. Talk about the state of that system. So it depends on the state of the system, not on the way the system reached that state. For example, if X is a state property, then we have a delta X, which will be X final minus X initial. X final, X initial. That will be the change in X. We also have a reversible process. Reversible process. A process can be said to be reversible if with a small force, if an infinitesimal force is applied to it, and then the process is reversible. So a process is said to be reversible if it's carried out infinitesimally slowly, so that the driving force is only infinitesimally greater than the opposing force. You have a force. You know that when we were in nursery or primary school, we used to have that game they call the seesaw. Seesaw. If your opponent, if you're a little bit, if you exert a little bit weight or force greater than your opponent, it comes down. And if he also exerts a little bit of force also, and then the thing also goes down on its own side. So when the small is so small, it's infinitesimally small, you apply it to it, then the system is said to be reversible. It's said to be reversible. And for such a reaction to take place, you will need time. You need time. You need time for it to happen. Unlike a irreversible process, this is a process that cannot return both the system and the surroundings to their original conditions, no matter what you are doing to it. So irreversible process, a process that cannot return both the system and the surroundings to their original conditions. To their original conditions. So now what we are going to be looking at, we want to be looking at work. And we know it already. So work is defined by mathematical relationship. Work equals force times distance. Work is force times distance. Work is force times distance. And then the units of force is the Newton. And you can also break it down. 1 Newton is 1 kilogram times 1 meter per second squared. So energy and work have the same units. Please note, work equals force times distance. Work equals force times distance. And we know force is Newton. So you will see there are so times distance, which is a meter. And then when you break it down, so you have a kilogram meter square per second square. Please note all these units. They are very important. Very, very important. They are very important. Now let's look at thermochemistry. And this is talking about the chemical energy changes in chemical reactions. So chemists define work as directed energy change resulting from a process. So our chemical reactions, they are always accompanied by either absorption of one form of energy or by release of one of it. So you will have to be electrical, but in chemistry, we are really concerned with chemical energy. And we're also looking at the work that can be done by chemical reactions. That's what we'll be looking at. That's what we'll be looking at. So the study of the energy change associated with chemical reactions is known as thermochemistry. Please note that thermochemistry is the study of the energy or its change associated with chemical reactions. Associated with chemical reactions. And then Tama Energy, want to look at Tama Energy, want to look at heat, want to look at temperature. So Tama Energy is the energy of motion. Like I told you, energy of motion is kinetic energy of the unit particles of a substance. So the unit particles of any substance is not at 0 Kelvin. So they have thermal energy. And the unit particles of a solid are in close contact, and movement of subparticles is limited to rotational and vibrational, which is because it's already solid. It's solid, so it cannot flow. Particles in a liquid exhibit all 3 types of molecular motion. It can undergo translational motion, rotational motion, and vibrational motion, even though they are in constant contact with each other. And like we have been taught in our secondary school days, the particles of a gas have the greatest freedom of all the 3 states of matter. You know, the 3 states of matter, we have a solid, we have a liquid, we also have gas. So of all these 3 classes, only your gaseous state has the greatest freedom out of the 3 states of matter. And they move freely about in space. So, and the higher the temperature, the faster the particles will move. You must have learned this, equally in your physics or by my colleagues who have taken you before me. Now, temperature. So if you look at temperature, it's only telling you a measure of how hot or how cold an object is. And what is really measuring is just the average random motion, the average kinetic energy of the unit particles of an object. So we can also define temperature as a property of an object that determines the direction in which thermal energy will be transferred when it is in contact with another object at a different temperature. What this one is saying is this: if you have 2 bodies, if one is hotter than the other, the flow of energy will flow from the higher one to the one that has a lower temperature. So until the two comes to an equilibrium. That is, when two objects are in contact with one another and at the same temperature, the average kinetic energy of the unit particles of the two objects will be equal. If you measure with a thermometer, it will be equal. But if there are different, from the higher one to the lower one. So temperature change is explained as a change in kinetic energy. Assuming one asks you that a temperature change is due to, number one, maybe A, kinetic energy, A or B, potential energy, C, electrical energy, and then D, nuclear energy. You should know which one to take. You should understand that. So temperature depends on the quantity of heat, Q, flowing out or in of into the system. It's flowing out of a system or it's flowing into a system. Please, you need to note that. You need to note that. Heat. Heat as a symbol Q. This is the Tama energy that flows into or out of a system due to a temperature difference. But you need to understand that. You need to understand that. Heat with a symbol Q is the thermal energy that flows into or flows out of a system due to difference in temperature. Therefore, from what we have just said, so it implies that heat will flow spontaneously from a warmer object to a colder object. So it flows from the warmer object to the colder object. Just like I told you, the direction of flow can be predicted. It can be predicted. Internal energy. Internal energy. The internal energy of a system, in some textbooks, the symbol is E, in some it is U. So it can be, you can see it either symbolized by U or E. The internal energy E, the potential energy of all the unit particles or molecules or ions of the system. So you can have EK plus EP. So it is made up of different energy. That it is peculiar to that system. So, and they are measured in joules. So, Tama energy, so it's associated with random molecular motion. And we have three types, like I told you, we have translational, rotational, and vibrational. Then the potential energy is the associated with electric attraction between molecules. They are molecular forces that need the bonds in chemical compounds, and then intermolecular forces. Intermolecular forces. And then we look at you will see delta, that object that looks like a triangle. So That object that looks like a triangle is known as delta. So, and that one is used to indicate or to symbolize changes in state functions. Changes in state functions. For example, delta E is talking about the E final minus the E initial. Minus the E initial. That is, you are subtracting your E initial from your E final. And this is the change in internal energy between the initial and final states. Between the initial and the final states. And when you have a positive value, that is in a state where your delta E is greater than 0, and that shows to you that your internal energy has increased. That is, energy is already added to the system. There is a transfer of energy from the surrounding into the system. So energy is added to the system. And in a situation where you have your delta E less than 0, you have is less than 0, it means energy, internal energy has decreased. That is, the energy is leaving or has left the system to the surroundings. Basically, let us note that again. Your delta E is greater than 0 means the energy has been added to the system. That is why it is now positive. It's sort of to the system. And where your delta E is less than 0, then that means your internal energy has decreased. That is, it has lost energy. That is, energy has left the system into the surroundings. So, thermodynamics and equilibrium. Maybe we should stop here today, and then we'll continue by God's grace tomorrow between the hour of 5 and 6 in the evening. Between the hours of 5 and 6 in the evening. So we'll meet tomorrow by God's grace between the hours of 5 and 6 in the evening. So good afternoon. Once again, my name is I.A. Adejoro. Adejoro, okay. Thank you. Thank you.